Hi all, I am Soham Jana, and today I'll be presenting my paper, joint work with Yury Polyanskiy and Yihong Wu on profile estimation of a finite population in possibly small sample regime. The setup is the following. We analyze an urn with k balls, each belonging to possibly k different colors, and we want to estimate the profile of the urn given by pi, where pi j gives you the proportion of color with exactly j balls. The sampling scheme we consider here is called the Bernoulli sampling model, in which we observe each ball independently with probability p, where p can be quite close to 0. We note that even though the empirical distribution of colors or the full distribution is actually more informative, in small sample regime, it actually cannot be calculated or consistently estimated. So we start with an example. Suppose we have an urn of size 17 with 5 blue, 4 gray, 2 orange, 3 red, and 3 green balls. Then the empirical distribution, call it mu, of the colors is given by the total number of balls for each color divided by the total size of the population. We note that the profile pi actually refers to the color deleted version of the urn, where we do not know how many colors are there or how many balls belong to each color. We only know that, for example, in this case, there are 2 colors with 3 balls each, and there are 3 colors with 5, 4, and 2 balls. This means we can calculate pi to give us that pi 3 equals 2 over 17, because there are 2 colors with 3 ball each, and pi 2, pi 4, pi 5 each equals 1 over 17 by the same reasoning. We note that pi naught actually gives us the total number of distinct colors, as pi naught equals 1 minus the total number of distinct colors divided by the size of the population. What is use of pi? So we note that a lot of important properties such as entropy, number of distinct species of the population are actually label invariant, or in this case color invariant. So they can actually be learned through pi. When the sample size is actually a vanishing fraction of the population size, we already noted that the full distribution of color actually cannot be estimated consistently. But interestingly, in a lot of small sample regime, consistent estimation of pi is actually possible, which implies in those regime we can actually have good information about those label invariant properties that I mentioned. The problem of estimating pi is also part of the program of empirical Bayes posed by Robbins in 1950s. Suppose we want to estimate some functional f of theta, and we want to compete with the oracle estimator f hat, which one can compute when pi is known. In case of unknown pi, we can just replace pi by an estimate pi hat and hopefully get a good estimator. Now the question is how good the estimation of pi can be done. So we first note about some existing work that is related to our paper. We first note the distinct elements problem, which is equivalent to estimating pi naught and has been dealt before by a long list of work. We note that Wu and Yang in 2018 show that when p is much larger than 1 over log k, then the optimal rate of estimation is polynomially small in k. They also show that when p is much smaller than 1 over log k, then consistent estimation of pi naught is actually not possible. In our paper, we actually improve the existing result and show that for other atoms of pi, for example, pi m when m is smaller than log k, then we also can get polynomially small rate in estimation. For m being constant multiple of log k, we show that the estimation is much harder and the rate is much bigger than 1 over log k whole square. So in our paper, we actually deal with a much bigger problem where we estimate pi in total variation distance. We note that even though the exact problem has not been dealt much before, there exists a long line of work for estimating the sorted version of the empirical, call it mu arrow. And we note that this sorted version and pi are actually closely connected. Valiant and Valiant 2013 showed that for general population, we actually can estimate the sorted version within a risk of 1 over square root of log k, which implies that for estimating pi also, there might exist a good estimator which gives us risk no more than 1 over square root of log k. But note that this result has been established for general population where the population size can be infinite, For finite population size, we show that we can actually improve upon this result by a square root factor. So what is our result? We show that for large k and constant p, the upper bound on the risk is actually 1 over log k times some constant and is achieved by a minimum distance estimator that can be computed in polynomial type. We also show that for constant p, the risk can be bounded from below by 1 over log k times some constant. And this shows that in linear regime, when p is some constant, the optimal rate of estimation is actually of order 1 over log k. The upper bound also shows that when p is vanishing, say omega 1 over log k, then we actually can consistently estimate pi as well. So what is the connection to the minimum distance estimator that we mentioned? So think about a general set of theta with a general distribution family p theta and norm of distributions rho. Then suppose we want to estimate the risk for pi under a general setup with some cost constraints, and the data is generated independently from p. Then we can think about an empirical estimate, call it nu hat, where we just plug in xj in place of theta j, and we note that this empirical estimator actually has mean equals to pi p, so it is unbiased for pi p. So we can think about some minimum distance estimator pi hat, where we take nu hat and pi p, get its distance in terms of rho, and then optimize it over all such pi that satisfies the cost constraints. Now we note that if additionally the empirical estimator nu hat has some concentration properties, then we can come up with some linear program delta that bounds the risk from above. The beauty of choosing total variation distance is this: when rho is equals to total variation distance, then the same linear program can be used to bound the risk from below. In our case of Bernoulli sampling model, we note that the family of distribution P is actually given by a Markov kernel, with each entries given by some binomial PMFs. We note that in total variation case, the linear program actually has a total variation version, which is of modulus of continuity type that pops up a lot in a lot of statistical estimation problems. Now we just show that this linear program delta TV can actually upper bound risk and as well lower bound it also. We show that the risk is bounded from above by delta TV evaluated at log k over k square root of that, and it is bounded from below by delta TV evaluated at 1 over k. Next, we show that the linear program delta TV actually has a logarithmic dependency on its argument, which gives us the risk bound that we are looking for. So we finally just prove bounds on delta TVT and then get some good results on the risk. So to bound delta TV, we first note that delta TV is a much more difficult linear program because it depends on optimizing over a set of PMFs. So instead, we try to relate it with another linear program, call it delta star, which is defined in terms of generating functions and possibly can be computed easily as well. To define delta star, we first define the A norm of any analytic function g given by the sum of the absolute values of the power series coefficients of g. Then we define delta star as the supremum of A norm of all analytic functions f that satisfies that the A norm of f prime is bounded by 1 and the A norm of certain p transform of f, call it fp, given by f of p bar plus pz, where p bar is 1 minus p, is bounded by t. And we note that delta star and delta tv are actually quite closely related. So we just bound delta star using some complex analytic methods. To upper bound delta star, we first note that for any feasible function f, the objective function can be written in terms of the sum of the power series coefficients of f, and the contribution that comes from the tail part after terms bigger than log 1 over t is actually of the order 1 over log 1 over t. and this can be proven easily by using the constraints on the derivative. For each of the previous term, we actually defined separate linear programs that maximizes the coefficient over the similar constraints in delta star, and find out that these small linear programs actually bound delta star from above. So finally, we just show that these individual linear programs actually are negligible in value, and we use Hadamard's three-line theorem for the proof. So what is Hadamard's three-line theorem? We first write down the sup norm over a complex set C, call it H infinity C, and denote by D the unit disk and the Horde disk dp, which is some scaled and shifted version of the unit disk. Then for any two Horde disks that are situated inside the unit disk, we note that the Hadamard's theorem says that the supremum of any analytic function f over the middlemost Horde disk can be bounded from above in terms of the supremum of the same function over the unit disk and the supremum of the same function over the innermost Horde disk. So when we get back to bounding delta m, we get that by the ordering properties of between a norm and the sup norm over the unit disk, we can use the constraints on delta m and the Cauchy integral formula to get bound on the sup norm of f over unit disk and the disk dp for any function f that satisfies the constraints in delta m. We also note that the objective function can be bounded by the sup norm of f over the Horde disk d half. When p is smaller than half, then we note that we get the required inclusion of Horde disk that we want for applying Hadamard's three-line theorem. And we note that then the objective function can be bounded in terms of the sup norm of f over the unit disk and the sup norm over the Horde disk dp. For p bigger than half, the bounding part is much more trivial. And finally, we combine all these bounds to get 1 over log 1 over t bound on the sum of the linear programs as well as the delta star t linear program. So finally, we present the proof on lower bound of delta star. We note that using the similar inequality between the sup norm over the unit disk and the norm A, we actually can relax the constraints and objective function of delta star to get a related linear program delta H infinity. We note that delta H infinity is much more easier to solve. It has similar value as we are looking for to establish on delta star. And we note that the value of delta H infinity is actually achieved by some exponential function in t. We then just modify the exponential function by some linear transformation to get a feasible solution to delta star. Finally, we note that the coefficients of the modified function can actually be related to the Laguerre polynomials, and then we just use the properties of the Laguerre polynomials to get a good lower bound on delta star. So finally, we summarize our findings. We find that the profile of population actually gives important information about a lot of good properties of the distribution. In small sample regime, when p is of order omega 1 over log k, we can actually consistently estimate the profile. When p is constant, we can actually find the minimax optimal rate. And we achieve this optimal rate by using some minimum distance type estimator, which can be computed in polynomial time. And we solve some infinite dimensional linear program for finding this estimator. Thank you.